In 7.5, we are going to talk about Taylor series and polynomials. And it's really important that before you watch this video, you actually go watch this 3 blue, 1 brown Essence of Calculus Taylor series video that I posted in Google Classroom, but you can also just Google it or look it up on YouTube. But that video is really going to explain the why behind what we're about to do. What we're going to focus on in this lesson is not so much the why, but the how do I actually do this. So if you have not watched that video to really understand why we're allowed to do what we're allowed to do, why we're allowed to use a Taylor or a Maclaurin series and a polynomial, I actually want you to pause this video and go watch that video and then come back to this video and unpause it. So one of the big ideas, or the idea, I guess, in general about a Taylor series is that a Taylor series gives us a way to model a differentiable function using a series in the neighborhood of some chosen center value C. So I just want you to stop and think about that and think back to the video. What we're actually being able to do, being allowed to do, is model something much more complicated like e or sine or natural log, modeling some function that is more complicated and may in the real world be more difficult to work with. We're allowed to model that using a Maclaurin or a Taylor series. And that idea in and of itself is really, really cool, but I also think that it's sort of hard to believe, which is why I really wanted you to watch that other video before we jump into these notes. So we're going to focus now on the structure of how do we actually model a function using a Taylor polynomial or a Taylor series. So again, the big idea here, what are we actually doing in this section? We are using a Taylor polynomial, or we can use a Taylor polynomial to approximate the value of a complicated function in the neighborhood of a chosen center C. So we can use a Taylor polynomial, which is finite, right? Polynomials are not infinite. Polynomials are finite. We can use a finite polynomial, a Taylor polynomial, in order to approximate the value of a more complicated number, again, in a specific neighborhood. So I think the really distinct and most important difference between a Taylor polynomial and a Taylor series is that a Taylor polynomial is finite, and because it is finite, it is an approximation of the value. So we could approximate cosine or sine or e to some value using a certain degree Taylor polynomial. As opposed to if we start talking about a Taylor series, we use a Taylor series, the word series right there, and you know in calculus we're talking about an infinite series. We use a Taylor series to model a function exactly in the neighborhood of that chosen center. So we're actually saying that this is infinite, since we're only talking about infinite series. This is infinite, and we can actually say that the function is equal to this sum, as opposed to with a Taylor polynomial, we can only say that the function is approximately, or we can approximate the function using that polynomial. So notation-wise, you need to be really cautious to make sure that if you're talking about a series, you're using an equal sign. If you're talking about a Taylor polynomial, you're using an approximately symbol when you're relating that function to the polynomial that you're creating. And then a Maclaurin series is just a really special, specific type of Taylor series or Taylor polynomial. And that it's special because it is centered at, whoops, that's not a highlighter. It is centered at x equals 0. So this word, this Maclaurin polynomial term, Maclaurin series, you need to know that that means it is centered at 0. So really, if you look at these two notations down here, these are exactly the same as the one above, with the exception that we're plugging in C equals 0 into the terms that you're seeing above represented. So let's go ahead and jump into some examples so that you can actually see how we're going to use one of these series in order to approximate a function. So number 1 down here, and I'm going to zoom in just a minute, says use the definition of a Maclaurin series to find the Maclaurin series for f of x equals sine of x. And it says specifically to use the values from 0 to 5 as our n values. And remember, when we're talking about series, those n values are going to be whole numbers. We're not going to plug in 1/2 for n. We're using the integers or the whole numbers between 0 and 5. Okay, so I zoomed in here on this problem, and I just brought down this definition of a Maclaurin series so that we have that easily visible when we are doing this. So since we are using our numbers from 0 to 5, I'm going to go ahead and over here I'm going to put 0. I'm going to use different colors. I think you'll understand why in just a minute. 1, 2, 3, 4. I'm going to use the same color twice, and 5. And I'm going to show you now how we actually manipulate, how do we use this table. So I personally like to use this formatted of a table. You can see in your notes over here, there's another format that's really commonly used. I'm not even going to really work through that. You can check on my worked out copy of the notes if you want to see sort of how I set that up instead. But I just really very, very much prefer to work with this sort of vertical or elongated table here. So what are we doing here? We have our n values. Those were given to us in the problem. What goes in the middle of this table? In the middle of this table, we are talking about our function f of x. So originally, this first line here is asking for our original function. So n is telling us what order of derivative we are taking. So this is talking about the order of our derivative. And you can also see in the Maclaurin series over here, n factorial is going to show up in the denominator. So I'm also going to make note to myself that this is also, n is also going to come into play in the denominator. So looking at when n is equal to 0, n equals 0 is actually going to give us our constant term. It's going to give us our constant term because, well, actually, let me just show you here. So when n is equal to 0, that means we have not yet taken any derivatives. So what was our original function? Our original function was sine of x, and we have not taken any derivatives, so we're just going to leave it as sine of x. And then the third column is what we're plugging in. Since this is a Maclaurin series, that means it's centered at 0. So I'm going to plug 0 into sine of x. Well, sine of 0, we know, is just 0. So now if we go down to our next line, which I'm going to do in red, when n equals 1, we are taking the first derivative of our function. Well, the derivative of sine of x is cosine of x. And if I plug 0 into cosine of x, I get positive 1. So this is going to be my first degree term, because n, again, is telling us our degree and the order of our derivative. Next, plugging in 2, well, actually, before I plug in 2, the second order derivative, so the second derivative of sine, or I can just take the derivative of cosine, is going to give me negative sine of x. Negative sine of 0 is going to give me 0. So this is going to be my second degree term, or my second degree coefficient. Go ahead and pause the video and fill in the rest of this table. So you're going to be taking derivatives in the middle column and plugging 0 into those derivatives in the last column. So here we are. Our table is now filled in. Go ahead and pause the video and check that you have your table filled out correctly. So now let's look at how we can use this table to write the series, the Maclaurin series of sine of x. So we talked about how these n values are going to be the denominators of our fraction, n factorial. They're also going to show up here to the power of n for each individual term. And then what I want you to notice is that, let's use a highlighter here, that fn of 0, these are actually going to be the coefficients for each specific term. And I say that term, I use the word coefficient loosely in the sense that technically this whole thing would be the coefficient of that term, but it's going to be the coefficient, let's say, of the numerator. That would be more mathematically accurate. So that's where this row of numbers is going to show up, in the coefficient of the numerator. So let's start with just the first term. And I'm going to try and go slow so that you can really see what we're getting at here. So first of all, what are we saying? We are identifying what sine of x is equal to as a series. Here we go. I'm going to come down here so I don't run out of room. F of x, which is sine of x, I'm just going to make a little note of that underneath, is equal to, and we can say that is equal to because we are writing a series, not a polynomial. We are writing a series, so we can use an equal sign. If we were writing a polynomial, we would use an approximately symbol because we're not saying that they are equal everywhere. Okay, our first term is going to be, and I'm going to do this in purple because I'm using that purple row in the table, the top purple row, is going to be the coefficient 0 times x to the power of 0, that's coming from my n value, over 0 factorial. And I'm going to go ahead and just right away simplify this, right? This whole thing is just going to go to nothing. Remember that 0 factorial is defined to be 1, so this is really 0 over 1, and there's no issue with that here. Let's look at the next term, which is in red. So I'm going to add to this my coefficient here, which is 1, times x to the power of 1, since that we're in the first row of our column, over 1 factorial. Let's go to the third column. So again, everything I'm doing is just coming from right here in this box. So my third term is 0 times x squared over 2 factorial. And then down to my third row, plus negative 1 times x to the third over 3 factorial. Plus 0 times x to the fourth over 4 factorial. And then lastly, let's squeeze this in here, plus 1x to the fifth over 5 factorial. And for right now, I'm just going to write plus ... We are going to get to our general term. I am going to talk about that in just a minute, but I want you to stop and see where this goes, and then go ahead and pause the video and simplify this and get rid of all those 0 terms. Just simplify this down as much as you can. So that should give you that f of x is actually equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial plus ... And it doesn't matter if this is a plus or a minus, right? Because whatever comes next, the sign could be impacted by our general rule. Now, this particular problem does not ask you for the general rule. And I am going to strongly recommend that if a question doesn't ask you for a general rule, that you don't give one. Because if you incorrectly identify the general rule, you're going to lose points. And if the question didn't ask that, you're doing extra work, you're wasting time, and you're putting yourself at risk for getting something wrong that the question isn't even asking you about. But I do, for purposes of us just having some extra practice, let's pretend that we did need to write the general rule. And let's go ahead and, oops, that first term is positive. Let's go ahead and write the general rule. So I'm breaking what I just said, and I'm saying, since we didn't have to do this. Again, it looks like this is alternating, so I could put minus ... It doesn't matter because the sign is going to be impacted by what your general rule is saying. So since the sign is alternating based on this pattern, and that makes sense considering what we're talking about here with sine and cosine, in order to make this alternating, I need to have a negative 1, and I either need to have negative 1 to the power of n, or I need to have negative 1 to the power of n plus 1 or minus 1. Since I want my first term to be positive, I'm going to make this negative 1 to the n minus 1. Because then if I plug positive 1 in here, I get negative 1 to the power of 0, which is going to give me a positive number. And the more you work on these general rules, the better you will get at figuring out exactly how to write them. It takes some practice. So now let's look at what's happening with my x's. Notice that all of the even powers are going to 0. So I want to write a rule that doesn't include all of those even powers. So I need to write a rule that impacts my exponent in a way that I always get an odd number. So thinking through that, if I wanted it to be an even number, I would always make it 2n. If I want it to be an odd number, I'm going to make it 2n minus 1. And before we move on to the denominator of the fraction, let's just check that this works. When I plug in 1, I should get x. So if I plug in 1 here, I'm going to get a positive. So negative 1 to the power of 0 is going to give me positive 1, which is what I needed. If I plug in 1 here, x to the power of 2 times 1 minus 1 is x to the first power. That's what I needed. And what I want you to notice is that each of these denominators is exactly the same as the exponent. So, but factorial. Ooh, I left off a factorial there. Shame on me. So that's going to give me 2n minus 1 factorial. And then you need your plus ... And remember how incredibly important it is for you to have this notation both before and after your general term to show that this does go on forever. So if you are asked, and only if you're asked, to write the general rule, make sure that you're spending that time to write it out and check and make sure it does actually fit with what you are saying in your function and series. So I also want to stop for a minute and just reflect on what we just did. We just took sine, the function f of x equals sine of x, and we said that we can represent this function as this series. And that's kind of awesome. We're saying that sine of x, which is not necessarily the easiest function to work with, depending on how we're using it, that we can represent it using this polynomial-like series, which makes it much easier to manipulate. And what I mean by that is, what if I asked you to approximate what sine of 6 was? Now, I don't know about you, but I would be pretty quickly reaching for my calculator to figure out what that is. But what we're saying is that you could use a Maclaurin polynomial, if we wanted to shorten this, to approximate that value, or you could use this series representation to give an exact value of sine of 6. All of your x's would become 6's. And you're going to see what I mean by that on example 2. But I just think it's so important to stop and really look at what we just did and how cool it is that we're saying that sine of x is equal to this infinite series. Now let's go ahead and look at number 2. All right, number 2 says use the definition of a 4th degree Taylor polynomial, key word here, meaning you should automatically be thinking approximately, for a Taylor polynomial centered at x equals pi, which you're going to notice there is now a pi here, for f of x equals cosine of x. Use 0 is less than or equal to n is less than or equal to 4. So based on all this information that we were just given, we're going to go ahead and fill in the table. So I know that my n values are going to go 0, 1, 2, 3, 4. I know that my original function is cosine of x, and then I'm going to take derivatives, so negative sine of x, negative cosine of x, sine of x, cosine of x. So I'm going to get all of my derivatives in there. And then I'm going to evaluate each of those derivatives in the middle column at pi. So cosine of pi is negative 1, negative sine of pi is 0, negative cosine of pi is positive 1, sine of pi is 0, cosine of pi is negative 1. So go ahead and pause the video, make sure you have this table filled in correctly, and then we're going to create our polynomial using that table. All right, so our 4th degree Taylor polynomial, and we can say that this is going to be negative 1 is our constant term, but I'm going to write out sort of the middle part anyways. Negative 1 times x minus pi, since we are centered at pi, every term should have an x minus pi, x minus pi to the power of 0 over 0 factorial. Now, I think that most of you probably could have written negative 1 knowing that everything else was going to go away since this is our constant term, but I just want you to see how I am still, even if it doesn't look like it, plugging into this nth degree Taylor polynomial. Also notice I have an equal sign here because I'm calling this a polynomial. I did not at any point in time say that cosine of x or that f of x is equal to this. When I'm talking about that, I will use an approximately symbol. Just wait and you will see that part. So our second term, our 1st degree term, is going to be plus 0 times x minus pi to the first power over 1 factorial plus 1 times x minus pi squared over 2 factorial plus 0 times x minus pi to the third over 3 factorial. And lastly, minus 1 times x minus pi to the fourth power over 4 factorial. Now, a couple things I want you to notice. I did not put a plus ellipses at the end of this. This is a polynomial. It is finite. It should not go on forever and ever and ever. It should go on until it tells us to stop, which is indicated to us in this problem by limiting the values of n. Also, most of the time it's just going to tell you we're looking for this degree. We're looking for a 4th degree Taylor polynomial. So let's clean this up a bit. We can simplify a whole lot of things here. So we can say that the polynomial of degree 4 of x is equal to, well, this whole term is just going to be -1. My red term is going to go to 0. My blue term is going to just be x minus pi squared over 2 factorial. My green term is going to go to 0. And my purple term is going to go to negative x minus pi to the 4th power over 4 factorial. So here I have my Taylor polynomial. Another way that you might see this written instead of the p sub 4 of x, you may also see it written as t sub 5 of x, t standing for Taylor polynomial. It's just good to be familiar with both of those notations in case you see it one way or another on an assessment question. So what we can say is that f of x is approximately this polynomial. So if we're relating back what we just found to the original function, we have to use that approximately symbol. If we're just talking about what the polynomial is or defining it, we can use an equal sign. And when we're using a series, it's always going to be an equal sign. So that was the first part of this question. The second part of this question says, use your polynomial to approximate cosine of 3. So here's what we can say, and this is what I think is really cool. Cosine of 3 is approximately -1 plus 3 minus pi squared over 2 minus 3 minus pi to the 4th over 4. We can actually say that cosine of 3 is approximately this value. So go ahead and grab your calculator and plug in -1 plus 3 minus pi squared over 2 plus, oops, I am missing a factorial here on this 4 and on this 4. Shame on me. Go ahead and plug this into your calculator and get this number on your calculator. So I'm going to say what this is equal to. And when I do this on my calculator, I am getting 0.9899928. And I forgot to put the negative in front there. Let's squeeze that in. Negative 0.989999928. And now what we did, again, to do what we just did, we said that cosine of 3 is approximately the Taylor polynomial that we just created, P4 of 3. So we took 3 and plugged it into our polynomial. Now what I want you to do, and that's how we got this value, is I actually want you to grab your calculator and I want you to type in cosine of 3 on your calculator and I want you to see what you get. So when I push this on my calculator, I get 0.989924966. So we approximated cosine without using a calculator, and it was the same to 1, 2, 3, 4, 5 decimal places. 1, 2, 3, 4, 5. That is crazy accurate, especially since College Board only really cares about things being accurate to 3 decimal places. Going all the way out to 5, we were able to approximate cosine without actually having to use a calculator to evaluate individual things. We might have used a calculator to figure out what 3 minus pi squared was or 3 minus pi to the 4th was, but this approximation, that was really the level of calculation that was required. And I just think that that's really, really interesting and cool and is going to lead us very much into the next section of our notes 7.6. But before we get into 7.6, I think we need to spend some more time really practicing and analyzing how a Taylor function or how a Taylor polynomial is set up, how it works, and really just do some more practice with it because this is an incredibly important topic in BC. So let's look at the examples on the next page. Okay, number 3. Find a power series for f of x centered at c equals 1 if f of 1 is 2 and the nth derivative of f at 1 is n plus 1 factorial. So I'm going to go ahead and set this up using the table that I've been using, except the middle column is going to be basically irrelevant for us. And the reason it's going to basically be irrelevant is because we don't actually know, we don't have a function to take derivatives of. So I'm going to just put a big question mark there. You don't even really have to include it, but I kind of want to keep with the standard that I just set on the front. So here's my table. Some things to tell us. If they are telling us, or some things they told us, I should say, that f of 1 is 2, that means that when n is 0, that's our constant term, the function is 2. Then they're telling us how do we find each next term. So let's find the first, second, and third term here. Move that a little bit to give myself more room. So the first term, if I plug in 1, the first term is going to be 2 factorial. And when I say first term, I mean the first term that has a variable. And then if I plug in 2, that's going to give me 3 factorial. If I plug in 3, that's going to give me 4 factorial. If I plug in n, that's going to give me n plus 1 factorial, just like the rule explained over here. So again, this is what happens when n is equal to 0. That's my constant term. The fact that they're telling me that this is centered at c equals 1 means that each of my terms are going to have an x minus 1. So find a power series for f. F of x is going to equal, because we are finding a series, 2 times x minus 1 to the power of 0 over 0 factorial. Again, I think you could just start by writing 2. You don't need to write all of that extra out. Plus 2 times x minus 1 to the first power over 1 factorial. Plus, and I just wrote 2 instead of 2 factorial because 2 is 2 factorial. So plus 3 factorial times x minus 1 squared over 2 factorial. Plus I'm going to bring my general term in on the next line where I clean this up a bit. So f of x is going to be 2 plus 2 times x minus 1 plus 3 factorial over 2 factorial is just going to be 3 plus Again, this question does not ask me for a general term, so I would stop right here to spare yourself the risk of making any mistakes. But since there is no risk here, since this is practice, if you wanted to write that rule, you could go ahead and write it. It looks like, I'm going to move my paper a little bit so that I have space. It looks like what's happening for the general term, and again, I'm not even going to add this to my answer. It's just good for you to think about it. You do need to have this plus ... over here. But the general term, what's happening? I have n plus 1 factorial, right? I had 3 factorial in the second degree term. I had 2 factorial in the first degree term. So what I have is n plus 1 factorial times x minus 1 to the power of n over n factorial. But this right here can simplify. This general term is really just n plus 1 times x minus 1 to the power of n. But again, I'm practicing this with you so that you can have extra practice on simplifying those general rules. I would not include that right now. I would draw a big X through this so that it doesn't get graded in case there is an error, but there's not an error. So let's leave that there. Go ahead and pause the video and spend some time, maybe 5 to 7 minutes, working on the remaining problems on this page. And then I'm going to bring you back and we're going to go over them together. I know this video is getting a little bit long, so I'm going to just kind of paste some of the answers in there, but I do want to walk you through them. Okay, let's look at number 4. The Taylor series of a function about x equals 3 is given below. What is the value of f, the third derivative f, or f triple prime of 3? So remember that the way that this is set up, the way that a Taylor polynomial or a Taylor series is set up is that f triple prime of 3 times x minus 3, so this guy over here, f triple prime of 3 times x minus 3 to the third power over 3 factorial is going to equal that cubic term, the term that's in that spot in the polynomial that they gave us. So let's look at the polynomial they gave us. They gave us this right here. So this is going to equal, let's give myself a little bit more room here. This is going to equal what they have in that third spot over here, 7 times x minus 3 to the third power over 3 factorial. So this is the same on both sides, which means that we can determine that this is equal to the only thing that's left. F triple prime of 3 is going to be equal to 7. So now let's look at the next problem. Find the second degree Taylor polynomial. Polynomial meaning that you need to use that approximately symbol, or that you could write this as p sub 2 of x. For f of x equals tangent of x centered at x equals pi over 4, use your polynomial to approximate f of 0.75. So here in the table I have 0, 1, 2, since we're looking for a second degree Taylor polynomial. I have my derivatives in the middle. I'm evaluating my derivatives at pi over 4 on the right hand side. So what I can say is either I can say tangent of x is approximately, or I can say p sub 2 of x is equal to, if I'm going to write it in polynomial form, both of those would be acceptable. And then you can see the work here for expanding it out and then for simplifying. As usual, you don't have to simplify. It was pretty easy to clean this up a little bit. And the reason I did choose to simplify this is because this question is also going to ask me to evaluate for 0.75. So I'm going to want it to be as simplified as I can in order to do that. So here I have f of 0.075, and then I plugged that in. Approximately simple again, and then you can see that value, and I plugged it in the calculator there so you can see the actual value as well. For number 6, we're using the Maclaurin series Maclaurin series centered at x equals 0 for g of x equals e to the 3x. So if you haven't already, go ahead and set up that table, find your values, and then plug them in. So again here, you can say that g of x is approximately, since we're using a Taylor polynomial, or since we are being told to use a fourth degree, you could say that this is t sub 4 of x is equal to that, or p sub 4 of x is equal to that. You just need to be consistent. If you're saying the function, then you need to have an approximately symbol. If you're naming it something else, like the fourth degree Taylor polynomial, t sub 4 of x, then you can use an equal sign, and you should use an equal sign. So the key thing here, the little tricky part is here, we're being asked to approximate e of 0.03. So once we have our polynomial, which we have here, to approximate that for e to the power of 0.3, we need to figure out what our x value is. So g of x is e to the 3x, and we want e to the 0.03. So we really need to figure out when 0.3x is equal to 3x. So x is going to be 0.01, and I want you to see where that came from, because that is what's going to get substituted into this polynomial in each of those different places to give us our approximation. And then I just think it's really cool to compare the approximation to what we actually get when you just type that into a calculator to see how stinking close those two numbers are. Okay, number 7 is giving you a Maclaurin. Let the Maclaurin series be defined. So they're defining it for you. Part A is just asking you to find the first 4 terms of the derivatives. So you're just going to take, oops, I didn't mean to move the paper. Sorry about that. You're going to take the first 4 terms here, and you're going to take the derivative of them. Since it says non-zero, you actually need to go out 1 extra term, so you might need to use the general rule to figure out what the 4th term was, so that when you differentiate that, you get the 3rd term. So that's listed there. Then they're asking you in part B to use that second degree Taylor polynomial that you came up with, or to use a corresponding second degree Taylor polynomial to approximate f of 2 and f prime of 2, so you can see that happening here. So go ahead and pause the video and check it out. And then in part C, you're being asked to write a linear approximation, as you can see there. Or you're being asked for the equation of the tangent line, not a linear approximation. Number 8 is going to ask you to use a calculator to do this. So what you need to do is in your y equals form, you need to put arc sine. Then, so y1 is going to be arc sine of x. y2 is going to be the derivative of y1. y3 is going to be the derivative of y2. That's how you're going to come up with these values in the table, and then you're going to expand it out and write that polynomial, that Taylor polynomial. So I hope that you found this video helpful and also just really interesting and exciting what we are doing with our Taylor series and polynomials. If you have any questions, make sure to write them down, and I look forward to supporting you on this in class. Thanks for listening.